Okay, so let's start. Today I'll talk about so-called Pfaffians. I'll talk about matrices over R. So let A be and real matrix. Assume that A is symmetric. Symmetric means its transpose is equal to its negative. Okay, so A plus A transpose is equal to 0. Let's see, for example, some examples. If A equals 1, so 1 by 1 is symmetric matrix. So A is something like this. Its transpose, of course, is equal to itself. Therefore, if A is equal to its transpose, a negative of its transpose, then this means A is just minus A is just A, and this is possible only if A is 0. So A 1 by 1 skew symmetric matrix is just 0. What about 2 by 2? So if A equals 2, let's say A is something like this, A, B, C, D, then the equation A transpose is equal to minus A gives us what? Gives us A, C, D, D is minus A, minus B, minus C, minus D. And from this, you see that A should be 0 and B should be 0 because D is equal to minus D, A is equal to minus A, therefore they should be 0. And B and C, so C is minus D, right? Or B is minus C. So this implies that A should be something like this. 0, B, minus B, and 0. Okay? So they are kind of very restricted set of matrices. And what will be Pfaffian? Pfaffian is like determinant. For example, consider this gadget. What is the determinant of this? Determinant is B squared, right? B squared. And this will be actually the general picture for skew symmetric matrices. And Pfaffian will be just square root of determinant. So for this matrix, for example, Pfaffian will be just B. Okay. You may wonder why something like this is defined, because as I said, Pfaffian will be just square root of determinant. So it's again a polynomial for the of the entries of the matrix, but it is defined only for skew symmetric matrices. Okay, Pfaffian will be defined only for skew symmetric matrices. And why it is important? Well, it naturally arises in other branches of mathematics, like geometry and topology. Okay, So Pfaffian is something actually very useful when you study, for example, topology or geometry. Okay, and it's of course, an algebraic thing. It is basically square root of determinant, and since it naturally arises in other branches of mathematics, it deserves attention. Okay. Peki. Şimdi let's see. Okay. Let A be who as well, maybe as before I do this, is it remark? You see, if remark, if and is about integer, and A is symmetric. And binary matrix, real matrix. Of course, I will talk about real matrices, real matrix. Then determinant of A is necessarily 0. Why is that? Well, this is because of the following. Determinant of A, we know that for any matrix is equal to determinant of its transpose, but in our case, A transpose is just minus A, because A is skew symmetric. Now, what is the determinant of minus A? Well, minus A means you multiply each row with -1. And you have n many rows. So n rows are multiplied with -1. Multiplying a row with -1 changes the sign of the determinant. But here you have n many rows multiplied with -1. So each one changes the sign with -1. And you have n of them. Therefore, this is just -1 to the power n times determinant of n. But n is an odd integer. Therefore, this number is just -1. So what we see is that this is just minus determinant of A. So determinant of A is equal to minus determinant of A. This is possible only if determinant of A is 0. Okay. So if A is an odd integer, then determinant of a skew symmetric matrix is not interesting. It is always 0. Okay. Therefore, we may concentrate on even dimensional matrices. Okay, so let A be a 2n by 2n skew symmetric matrix. And in geometry also, usually all these matrices are even dimensional matrices. Well, yeah. Okay. they are related so-called curvature tensor. So there is tensor also in geometry. And those tensors are two tensors. So they are like, you know, dx, wedge, dy, and so on. So you have, you know, alternating products, two forms, and they are represented by skew symmetric matrices. Okay. So skew symmetric means right, A transpose is equal to minus. All right. Now, as in this case, you know, if you just recall this gadget. Now, what is the characteristic polynomial of this gadget? You know, characteristic polynomial of this at A, so determinant of A minus X times identity. What is this? This is just determinant of minus X B minus B minus X. So it is just X squared plus B squared. And what are the eigenvalues? If you take this to 0, you see that X equals plus minus ID. So eigenvalues are not real. Okay, you have two complex eigenvalues, they are not real. Therefore, we shouldn't expect that so here we computed the characteristic polynomial of this matrix, and it is just X squared plus B squared, and eigenvalues are like this. So we shouldn't expect that this matrix is to be, you know, diagonalizable. And we will see that this is the general picture. Eigenvalues will be totally imaginary. So they will be numbers like this, no real parts. Eigenvalues will be I times well, this means what? We should work with complex numbers. How can we work with complex numbers if they are given a real matrix? Well, we can just cancel everything by C and work with complex vector spaces, and that's what are we going to do. Efendim? Evet.
Direkt oraya şey mi yapıyoruz? Karakteristik matrixler. Yani hani direkt determinantı şey yazsak mesela x, yani x yerine şey yazsak. Artı eksi işte determinant çarpı x.
Nasıl?
Yani hani mesela işte biz x'de square root işte determinant. Oradan bir yüklemiş. Hani direkt oradaki kökler var ya, artı eksi dy.
Evet.
Oraya onu yazsak direkt olur değil mi? Her matrixler. Yani bütün skew symmetric matrisler için olur.
Yok, şimdi göreceğiz onu. Yani skew symmetric matrislerin diagonalization'ı tabii reeller üzerinde olmayacak. Çünkü burada işte gördük yani reel eigenvalue'ları genelde olmayacak. Sıfır haricinde. Kompleks düşünürsek o zaman eigenvalue'ları olacak. Diagonalizable olmasa da işte şu forma gelecekler. Yani bu diagonal matris değil ama gene de işte güzel bir form. Peki şimdi görelim. So let's consider this skew symmetric matrix. Now consider A as a linear operator on Rn, R2n. Okay. Şöyle yani A'yı linear operatör gibi görüyorum. R2n'den R2n'e. ne yapıyoruz? Bir tane vektör alıyoruz. Sonra bir tek vektör and just send it to matrix multiplication by that. Well, they've seen that over there, such an operator probably has no real eigenvalue. But what we can do, we can just transfer this vector spaces by C and consider the whole thing over complex numbers. We may regard A as an operator on C2n. How? Well, the same formula, okay? C2n, C2n, and you take a vector here and just send it to A. Right? Any real number is a complex number. So these are also here entries of A are complex numbers. You just perform this matrix multiplication. This is actually what we are doing. We are just multiplying. We are taking tensor product of R2n with C over R. Okay, and then this vector space is just C here. We are just taking tensor product actually with C. All right. Now I can talk about eigenvalues and so on. Okay. And that's what we are going to do. Okay, now first claim is this. Any eigenvalue of this operator is totally imaginary, purely imaginary. Totally denmiyor değil mi? Pure imaginary. Tersi geliyor zaten. So what we mean if lambda is an eigenvalue, then its conjugate is just its negative, or it is something like this: I times let's say R, and R is a real one. So purely imaginary means this. Okay. Yeah, real part is. What is it? Well, this is easy. Okay. Well, you see, A is skew symmetric, but here, if I consider it as an operator on a complex vector space, then I should talk about whether it's a joint whether it's a self-adjoint or skew adjoint. Well, let's see what is this. Well, this is just conjugate transport, right? A is a real matrix, therefore its conjugate is itself, right? Entries of A are real, so this is just A transpose, but A is skew symmetric, therefore this is equal to this case. So as a complex operator, it is not self-adjoint, and indeed it's star A star is just minus. Okay, now let's continue. So let lambda be an eigenvalue for A. Why do we have eigenvalue? Because we are working over complex numbers. Its characteristic polynomial is a polynomial over complex numbers, and every polynomial over complex numbers has a root, and that root is an eigenvalue. So this operator has an eigenvalue. It doesn't have to be real; it's a complex number, and let okay, C2 and and associated eigenvector. Yani şu. A times B is just lambda B. Ne göstermemiz lazım? We have to show that lambda bar is just minus lambda. All right, let's see why that's true. Now, okay, now, since this is an eigenvector, B is not zero, of course. Therefore, the inner product of B with itself, here we are using the standard inner product on Cn. This is known B squared and it is always positive. Belki şeyi hatırlatayım. Nedir standart inner product'ımız? Yani U diyelim işte atıyorum Z1, Zn, B'de ya da W'da işte şey oldu. Bu. A1, A olsun. B1, B olsun. What is this standard inner product? Evet. So it will be the following. AI, EI, conjugate. I from 1 up to N. Well, in our case, okay, now if you have n many of them, then after bizim burada tabii 2 n olacak ama hani şeyse şunu düşünün, yani bu Cn'deki standart inner product. Şimdi orada ama ben şuna bakın. Lambda times norm V inner product. This is a positive number, but that is just the. Well, I can take this lambda inside, but this is the eigenvalue, vector for A with this eigenvalue, so this is just AB. And then I can just take this to the other side as A star. But A star is just, in our case, minus A. So it's just minus minus A. So lambda times norm V squared is equal to lambda V is just A is just lambda V, and this coefficient goes out as this is a Hermitian inner product. It will go out as the conjugate of this number, and then I have B inner product with B. So this is just minus lambda conjugate norm to square. But this thing is a positive number, therefore I can just cancel that. Therefore, what we see is that lambda is equal to minus of its conjugate. Well, this is possible only if lambda has no real parts. So this means lambda plus lambda bar is 0. Evet, yaklaştı. So this is finished. Therefore, if we have an eigenvalue, it should be purely imaginary. Okay? Like this one. Over here. Okay. Second claim is that if we have two eigenvalues of this skew symmetric matrix, and if they are distinct, then the corresponding eigenvectors has to be orthogonal. So, if lambda 2 are eigenvalues of A and AB1 is lambda 1 B1 and AB2 lambda 2 B2. So these are eigenvectors. B1 and B2 are eigenvectors. Then V1 and V2 are orthogonal. Okay. Proof is actually similar to the proof of the similar statement for symmetric matrices. Okay, we prove this for symmetric matrices. The proof we will do is basically the same. All right, so let's just start with lambda 1 times V1, V2. Okay. You know what I'm going to do, right? We will write it like this. But then this is just A V1 V2. Well, then that's equal to I can take this A to the other side as A star, and A star is just minus A because it is skew symmetric, minus A. AB2, this is also an eigenvector. It is just lambda 2, of course, lambda 2 times minus lambda 2 times 2. So what we see is that this goes out as lambda 2 conjugate V1, V2. Okay. So lambda 1 V1, V2 is minus lambda 2 conjugate V1, V2. let's just collect all the times on one side and see what we get. So from this, we see what? Lambda 1 times this plus, so this goes to the other side as plus lambda 2 bar. Lambda 3 bar. V1, V2 is equal to 0. Well, we said that lambda 1 and lambda 2 are distinct eigenvalues, but they are we know that they are totally, so they are pure imaginary. So if let's say lambda 1 is just I times A and lambda 2 is I times B, where A and B are real numbers, like they are numbers like this, pure imaginary, then what is lambda 1 plus lambda 2 bar? Lambda 1 plus lambda 2 bar is just I times A minus I times B. So this is just I times A minus B. But we said these are different. Lambda 1 and lambda 2 are different. So lambda 1 different from lambda 2. This is if and only A and B are different, right? So for this eigenvalues to be different, A and B should be different. Therefore, this is not 0. So this is not equal to 0. Well, so this number here is not 0. This is not 0. But this number times this complex number is equal to 0. So that implies this complex number to be 0. So this means what? V1 is orthogonal to V2 in this inner product, or I mean Hermitian product under the solution product. Tamam mı? Peki. Ne gördük? So we have seen that if in a skew symmetric matrix considered as a linear operator, its eigenvalues are purely imaginary and eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. We have one more simple fact. Explain another claim. If A, B equals lambda B, then of course, I mean, so this is an eigenvector. So eigenvalue and eigenvector. Then taking conjugate, so AB bar is just lambda 1. Yani bu ne demek? Yani aslında bu claim değil, bariz bir şey. So if D is an eigenvector, corresponding to some eigenvalue lambda, then V bar is an eigenvector corresponding to lambda bar. Yani bir tane elinizde eigenvalue ve eigenvektör varsa bir pair'i bedavaya elde ediyorsunuz, değil mi? Konjugelerini alın. İspat da gayet basit, of course. I have this. Just take conjugate of both sides. Okay. Well, this is a matrix. This is a vector. You multiply them and then take conjugate. But conjugation and multiplication can be interchanged. So I can just take conjugates and then multiply them. Why is that? Because you see, I mean, A times B conjugate is just A conjugate, B conjugate, right? So you can always do that. And the same thing here, just lambda bar times B bar. But A is a real matrix. Since it is real, A bar is just A. Therefore, A times B bar is lambda bar times B bar. Okay? A reel olduğu için konjugesi kendisine eşit. Ama bu vektör değişmek durumunda. Tabii eğer bu sıfır değilse, if lambda is not zero, then this is a purely imaginary number, and therefore V cannot be real vector because A is real. I mean, so this is real. If this is real, then this is a real vector. This is real, but this is purely imaginary. Therefore, this cannot be real. Therefore, the vector V should be also imaginary. I mean, it cannot be real. Tabii A reel. Yani onu en başta söylemiştik sanki. Yani onu A her zaman reel mi var? Efendim? Evet, yani kompleks anlıyoruz, hep reel. Tamam mı? Dolayısıyla ne elde ettik? Skew simetrik bir matrisimiz varsa bunun eigenvalue'ları var. Hepsi pure imaginary. Ve her bir eigenvalue'nun konjugesi de eigenvalue. Eigenvektörler de birbirlerinin konjugesi oluyorlar. Eğer eigenvalue'nun konjugesini alıyorsanız vektörün de konjugesini alacaksınız. Ve distinct eigenvalue'lara karşılık gelen vektörler de birbirine dikler. Bir tane daha fact'imiz var. O da yine ispat etmiştik. Simetrik operatörlerde. Neydi? Bir eigenvektör varsa ona dik olan eigenvektörlerin oluşturduğu alt uzay lineer operatörü altında invariant kalıyordu. Hani dik vektörler dik vektörlere gittiği için o yüzden de işte boyutu küçültüp işlem yapabiliyorduk. Şimdi onu yapacağız. Okay. Now, so we continue. Okay, şöyle diyeyim. Let three eigenvector for its eigenvalue lambda. So we have A times B is just lambda times B. Then we know what? Then A B bar is lambda bar B bar, right? So it's another eigenvalue and eigenvector. Since okay, assume that şöyle bir assume that lambda is not 0, then of course this is a purely imaginary number. Therefore, these are distinct eigenvalues. This is an eigenvalue. This is another eigenvalue. They are both purely imaginary. Therefore, they are distinct. And we have corresponding eigenvectors. B and B bar. We have two eigenvectors. And I know that these two vectors are orthogonal to each other. The inner product B bar is 0. This means that these two vectors are linearly independent. So therefore, so the subspace, let's say U, which is just spanned by D and D bar, is two-dimensional. Okay. Çünkü bu iki vektör lineer bağımsız. Şimdi bu vektörün, daha doğrusu subspace'in ortogonal komplimanını düşünelim. Aslında bir saniye öyle yapmasak mı? Şöyle yapayım. Böyle de yapabiliriz ama böyle yapmayayım. Şöyle yapayım. Burayı silip yani böyle de yapılabilir ama daha kesilmeli bir şey yapayım. Şöyle yapayım. Okay, forget this. Let's continue as follows. Yani gene okay, so let lambda be an eigenvalue and be an eigenvector for A. So A times B lambda B. Şimdi şunu biliyoruz. Diyelim ki lambda 0 olmasın. Lambda'nın 0 olmadığını kabul edelim. Yani Skew o zaman B vektörü de şey olmak zorunda değil. Buna gerek var mı? Esüm etmeye gerek yok. Şöyle. Şu vektörü şöyle yazalım. Şimdi lambdamız bir kere şöyle, değil mi? Bu purely imaginary. Diyelim ki bu şey olsun. I times A. Eigenvektörümüz de şöyle bir şey olsun. Eigenvektör Cn içinde. It has real and imaginary parts. let's say C is the real part and mu is the imaginary part. So both of these are vectors in METU and okay. So real and imaginary parts of the vectors. Then we have the following. A times V is just lambda times E. A times B is just C plus I times 2. And this is just okay. I times A and then C times I mu. So we have A times C plus I times A times mu. And what about this? So we have my I times I just minus 1. So minus A times mu plus A times I times C. Yes, sure. I times A C. Now, both of these vectors are complex vectors, right? This is a complex vector. This is another complex vector. But I know that A is a real number and these are real vectors. Now, this vector has real part this and imaginary part this one, right? Real and imaginary parts. And this is here the real part and this is the imaginary part. Since they are equal, this real part has to be the real part here, and this imaginary part has to be the imaginary part here. Therefore, A times C is just minus A times mu, and A times mu is A times C. Okay? So the real and imaginary parts of the eigenvector are switched by the operator A, right? A sends the real part to a multiple of the imaginary part, and A sends the imaginary part to a multiple of the real part. So it switches real and imaginary parts of the matrices, vectors. Tamam mı? İyi, ara verelim. Aradan sonra devam ederiz.